Hello everyone, myself Digvijay Ingle. In this session, we would be talking about our recent work that we submitted to the 5th edition of Black Box NLP workshop. The work is titled as Investigating the Characteristics of a Transformer in a Few Shot Setup. Does freezing layers in RoBERTa help? This work has been done alongside other authors, namely Rishabh Tripathi, Ayush Kumar, Kevin Patel, and Jithendra Vepa from Observe.ai. The talk has been organized as follows. We first start with our motivation. We then talk about the problem setup we operate in. We lay out our proposed approach. We then describe our experimental setup and share the results. And finally, we conclude based on our findings. Let's begin with the motivation behind our work. It is a well known fact that fine tuning bird style language models requires large annotated data. And collecting such a data is not only a time consuming exercise, but also involves huge annotation costs. This mainly prevents adoption of these models to real-world use cases, which further gives rise to another stream of research known as low-resource techniques such as weak supervision and zero or few-shot learning. While these techniques have proved to be immensely successful, their functioning still remains a mystery. How these language models adopt when fine-tuned on specific tasks, this question has been extensively studied in presence of large annotated data. But the question that comes up is, can we extend the observation from these studies to few shot fine tuning as well? And if yes, can we leverage them to train better few shot models, better and efficient few shot models? In our work, we'll try to answer some of these questions. Our work is primarily motivated from the findings of Fang et al., where the authors investigate the similarities and differences between representations learned by pre-trained language models and those learned by fine-tuning them on specific tasks. On the right, we have some of the results discussed by the authors in the paper. Specifically, figure B contains comparison of similarities in representations obtained from intermediate transformer layers of pre-trained Albert model and those obtained by fine-tuning it on a binary text classification task. Some of the key observations from the study include the representations at the initial layers are very similar to each other, whereas in the later layers we see stark differences. This brings us to another question. Do these findings also corroborate in few shot settings? This is where our analysis comes into the picture. We extend this study to compare and contrast the representations in fully supervised models and few shot models. Specifically, we work with RoBERTa based model. In figure A, the x-axis indicates the intermediate transformer layers of pre-trained RoBERTa based model, whereas the y-axis indicates the intermediate transformer layers of RoBERTa based model fine-tuned on SST2 task in presence of large annotated data. We observe similar findings as the ones reported by Fang et al. That is, the initial layers show representations similar to the pre-trained language models, whereas the later layers show stark difference, which means that most of the task-specific information is learned at the later layers, whereas the initial layers remain mostly unchanged. We extend a similar analysis to few-shot setup where we only have 8 training examples per class. The results from the analysis are presented in figure B. The observations from the study are very similar to those obtained when fine-tuning the model in presence of large annotated data. However, with a minor difference that the pattern appears a bit diffused. This could either be due to the inability of the model to learn from limited training examples or certain divergent behaviors while fine-tuning them in with very limited examples. A natural question that then comes up is, how does this translate in terms of accuracy? As a result, we perform a truncation study where we truncate the pre-trained RoBERTa based model and the one fine-tuned on SST2 task to understand the extent to which task-specific information is learned at these layers. We sequentially add a classification head on top of each of the intermediate layers and fine-tune only the classification head on SST2 task, with rest of the RoBERTa based architecture being frozen. As can be observed from the chart, the performance on SST2 task is almost the same for both the models at layers 1 to 6, implying the layers at the initial layers are hardly updated, whereas as we move from layers 7 to 12, we observe a drastic change in accuracy for fine-tuned model, which means that most of the task-specific information by the fine-tuned model is learned in layers 7 to 12. Hence, this brings us to another question, like since both fully supervised as well as few shot models show similar representations and performances at the initial layers, can we just freeze these initial layers to train better few shot models? We hypothesize that the lower parameter space obtained by layer freezing could in turn benefit the few shot models and train and help in training them in a more efficient fashion. Let's try to understand our problem setup. The task at our hand is to fine-tune the pre-trained language model L on task D with a label space C in presence of a k-short training data. What this means is we only have k training examples per class. As a result, the cardinality of the training set now turns out to be k into the cardinality of the label space. Additionally, we assume that we have an access to a validation set of similar cardinality. This is specifically required to adhere to the constraint of operating with very limited data. Also, we assume an access to a large test set solely for the evaluation of the model. In all our experiments, we restrict ourselves to RoBERTa base as the language model, and we experiment with k ranging from 8 to 64. Now, coming to the proposed approach, we freeze first n% of the transformer layers, where we begin with n equal to 0 and go all the way up to n equal to 100 in steps of 25%. So n equal to 0 implies fully trainable layers, implying all of the transformer layers can be trained, whereas n equal to 100 implies fully frozen layers. An important thing to note here is n equal to 100, in case of n equal to 100, we still have a classification head that is trainable, whereas rest of the RoBERTa base architecture is completely frozen. For the evaluation of the approach, we choose two metrics, basically macro F1 to evaluate the model performance, and secondly, training time to evaluate the training efficiency and convergence. The training time is calculated using an early stopping criteria, where we evaluate the validation loss at each step and stop the training when the validation loss does not improve for 5 consecutive steps. The datasets that we experiment with can be broadly divided into two categories. One, which is a binary text classification datasets, where we choose SST2, COLA, and subjectivity tasks. The other category includes multi-class classification datasets, where we experiment with AG News, SST5, and SNPs datasets. Coming to the experimental setup, we experiment with the vanilla fine-tuning approach. The reason why we choose this approach is it coheres with the standard fine-tuning approach for language models. And secondly, it is also reported as a baseline in most of the state-of-the-art few-shot approaches. To elaborate on the approach, we have a text sequence X, which is tokenized, which is then tokenized to obtain a sequence X hat. An important thing to notice, X is prefixed with a start of sentence token and suffixed with an end of sentence token. The language model L is then used to map the tokenized sequence to a sequence of hidden states in the d-dimensional vector space. Further, we have a classification head which takes the hidden representations of the start of sentence token and maps them to the probability distribution over the label space. Now let's take a look at some of the observations from vanilla fine-tuning approach. One key observation is that we observe that 100% layer freezing always leads to lower performance for all k values across tasks. Further, when we increase n from 0 to 50%, we observe that the F1 score gradually improves. When we further increase the amount of freezing, we see that the F1 score starts dropping. Similarly, when we look at the training time, we observe that the training time consistently reduces when we freeze layers, implying that freezing leads to better convergence by preventing any divergent behavior during model training. We also replicate the similar experiments on the remaining tasks and observe that the results are in line with the above observations. While these techniques show favorable results in case of vanilla fine-tuning, next question that could naturally pop up is, do these also generalize to state-of-the-art few-shot methods? And as a result, we try to benchmark them on two of the most popular few-shot methods, basically DNNC, which is a discrete nearest neighbor based classification approach. And the second one is LMBFF, also known as language models best friends forever. This DNNC uses a nearest neighbor classification approach, whereas LMBFF uses a prompting paradigm where a text classification task is transformed to a masked language model task, wherein the language model is prompted with natural language instructions to infer the class labels. Let's take a look at the observations from the experiments. For these experiments, we specifically restrict ourselves to two settings where we freeze first 25% of the layers and first 50% of the layers, since these are the settings which resulted in favorable outcomes in case of vanilla fine tuning. We track two metrics, basically delta F1 and delta time. In order to understand these metrics, let's take an example. The first entry in the table involves an experiment with k equal to 8, implying we have only 8 training examples per class. And the number 8.25 indicates that 25% of the, while we, a model with 25% of the transformer layer frozen leads to 8.25% better F1 as compared to a fully trainable model. Similarly, a 25% a model with 25% layer frozen leads to 56% better training time compared to a model with a fully trainable setup. The positive delta F1 across the table implies that freezing up to 50% of the layers generally leads to improvement in model performance over fully trainable layers. Now, this not only applies to the vanilla fine tuning, but also generalizes to the state-of-the-art few-shot methods. Further, the positive delta time across the table indicates that freezing up to 50% of the layer generally leads to faster convergence, not only in case of vanilla fine tuning, but also in case of few-shot methods. Finally, to conclude our findings, while freezing all transformer layers given a small annotated data could be a natural choice, our results show that this strategy never helps. Further, fully trainable layers also do not help, and hence partial freezing is definitely required. This is evident from the observations that freezing up to 50% of the layers generally led to improvement in F1. Further, our proposed approach is not only applicable to vanilla fine tuning, but also can be generalized to state-of-the-art few-shot methods. This is quite evident from the fact that 81% of the settings with state-of-the-art few-shot methods resulted in an improvement in F1 when up to 50% of the layers were frozen. Also, we observe up to 68% reduction in training times across our experiments, implying that the reduced parameter space indeed leads to faster convergence, which further has a broader impact on reducing carbon footprint. Also, we do not observe any clear pattern on performance when freezing up to 75% of the layers, and we hypothesize that this could be due to the proximity to the point of inflection where the behavior in similarity between representations changes. In future, we would like to extend the study to utilize the patterns in similarity representations to specifically curate loss functions in addition to cross entropy loss. We hope that this could in turn benefit training few-shot models. Further, we would like to explore this idea of layer freezing in context of low-resource multilingual models. These are some of the resources that we have utilized for our work. However, we would encourage everyone to go through our paper for more exhaustive list of resources. This brings us to the end of the talk. Thank you everyone and have a good day.